Welcome, I hope you're having a good day, and today I'm going to try to explain in simple terms what is matter. Well, you might hear a simple answer that matter is a thing which possesses mass. Well, what is mass? Well, mass can be defined as resistance to movement. Imagine we're in space. It's just us in space. There's nothing around besides a bowling ball and a ping pong ball. So you know a bowling ball has more mass than a ping pong ball. If you were to try to push the bowling ball, it's going to resist you more than the ping pong ball would. So in that manner, we have a way to quantitate this thing called mass, or quantitate resistance to movement. The harder it is to move, the more mass it possesses. So matter, you probably learned in high school, can be broken down into 3 elementary particles, which can be broken down further, but nobody knows what's going down on a further level. So matter ultimately is made up of electrons, which all call E-, protons, which all call P+, and neutrons, which I'll call N. N0 maybe. And a nucleus is made up of protons and neutrons. And in the early days, they knew there was just a nucleus that was positively charged. They didn't know it was made up of protons or neutrons, but they knew what electrons were. And I'm going to go over the historical development of how we found out that atoms are made out of these 3 constituents. So around 1890s or so, a man named J.J. Thompson performed the following experiment. There was known to exist a cathode ray lamp, it was called. You can just think of it as a sort of light bulb, and it would emit these sort of rays, which were called cathode rays. And nobody really knew what these cathode rays were. Well, what J.J. Thompson did was take one of these bulbs, and it's emitting cathode rays in every direction, and he put a single slit there. So you could effectively make a sort of gun out of your cathode rays. Well, he took those cathode rays, and he put them through an electric field, right? He put a bunch of positive charge on a metal plate up here, a bunch of negative charge on a metal plate down here, and those cathode rays were deflected ever so slightly up towards the positive plate. And now there was known a law at the time that said your angle of deflection, this angle here, is proportional to how heavy that thing is. So if we call this angle theta, well, we know theta is proportional to the inverse of the mass. So that means a more heavy object would deflect less. So imagine you have a bowling ball and you put it through this apparatus, it would only deflect, something like that. But if you take a ping pong ball and do it, ping pong ball would, go way off course. And in that way, J.J. Thompson calculated the mass of the electron as about 1,000 times greater than the mass of an atom. So he knew there was these things with negative charge because they were attracted to the positive plate, and they were about 1,000 times lighter than the mass of the atom, because they deflected a whole lot instead of a little bit. So now J.J. Thomson had a student called Ernest Rutherford, and around the 1900s, the first decade of the 20th century, Ernest Rutherford, he was working under J.J. Thomson, but then he left and went somewhere else and did his own experiments. He performed the following experiment. It was known that there were things that emitted so-called alpha rays. If you have a big ball of this stuff that was emitting alpha rays, so you could have this big ball of things that emits alpha rays in every direction, just like the lamp above emitted cathode rays in every direction. Well, Ernest Rutherford, learning under the great J.J. Thomson, he must have learned something, because what he did was take those alpha rays and put them through a single slit, just like J.J. Thomson put the cathode rays through a single slit. And what Rutherford did with these alpha rays was strike them onto a gold foil. So this is a gold foil here. And he picked a gold foil because a gold foil was very dense with gold atoms. So if we zoom in on the gold foil, we know it's composed of gold atoms, and it's very dense. So they thought there was very little space between each of these gold atoms. So now what Rutherford expected was the alpha rays would come in, and since they would hit a solid object, well, they would just bounce off that object and go backwards. What actually happened was the alpha rays, most of the time, they went through what was thought to be a solid object. Well, this made absolutely no sense. So I'll say a little bit more about how they thought, about how Rutherford at least, and Thomson thought about the atom at this time. So this was Thomson's theory of the atom. He thought you had an atom, and since he knew inside atoms there were these things called electrons with negative charges, he thought there was a bunch of negative charges inside this ball of matter. Well, if you have an electrically neutral ball, well, then you gotta have positive charges somewhere around. So there was this ball of positive and negative charge. And this was called the plum pudding model also. And I've never even seen plum pudding or encountered it in my whole life. I think that was a British thing. It's easier, at least if you're American, to think of it as cookie dough before you put the cookie dough in the oven and bake the cookies. So you have this positive cookie dough stuff that's smeared out, cookie dough, and it has positive charge. And then you have chocolate chips, say, in your cookie dough, and these are the negative charges. And this was what they all thought the model of the atom. This is what everyone back in around 1910 thought the atom looked like. So just like Rutherford was shooting alpha rays at these and expecting them to bounce off, well, turns out they didn't. So, okay, so we got a gold atom here again. And 99.99% of the time, Rutherford found the alpha rays, this is an alpha ray, would go through the gold foil. Well, about 0.01, or 1 out of every 1,000 or so rays would actually get deflected. See, what Rutherford was expecting was 100% of the rays would get deflected. That's not what he found out. And from this, Rutherford concluded, so he made a new model of the atom that said, at your center there's a very small concentrated thing of positive charge, and around that charge you have electrons. So that way, if you shoot something through it, most of the time that thing will just go right through because it's mostly empty space. But occasionally you'll get an alpha ray that will come in and exactly hit the nucleus and then bounce off. So in that way, Rutherford discovered that the nucleus is very, very small compared to the size of the atom. And to give you a sense, it's something like the nucleus, if the whole atom is a football stadium, the nucleus was found to be the size of an ant. So the nucleus is super small compared to the size of the atom. So we have electrons and the nucleus, which was not known by Rutherford to be composed of neutrons. That's what we had around 1910 or so. In the 1930s, James Chadwick discovered the neutron. And thus, completed, not really, that's the wrong word, completed. It kind of made a coherent picture of the atom in some sort of sense. Well, also around this time, say the 1920s, or actually in the 1910s, a man named Bohr knew about Rutherford's experiment. Niels Bohr, a Danish physicist, knew about Rutherford's atoms and agreed with Rutherford. And what Bohr did was say that, okay, so you have a nucleus in an atom, and the electron orbits that nucleus in a circular orbit, kind of how planets orbit the sun. That's what Bohr thought. So he said you have a positive nucleus and you have electrons going around a circle. And they might be very close to that nucleus, or they could be farther away, but they can't be anywhere in between, is what Bohr said. So they can be at this inner circle or this outer circle, but nowhere in between. Well, it was later found out that Bohr was incorrect, and that on average the electrons follow this inner circle or this outer circle, but it's actually the path of the electron is kind of smeared out. So if you tried to find an electron a little bit off this orbit, if you're close to the orbit, you're likely to find it. If you're further away from the orbit, you're a lot less likely to find it. Now, things got completely confusing when a man by the name Louis de Broglie, French guy, French physicist, he said, well, okay, so the whole time during this video, we've been treating matter as if it was made of particles, right? Things you can hold in your hand physically. Solid pool balls, but they're very, they're very small. They're solid things, they're particles. And remember in one of my previous videos, we talked about light and that it's a wave. Einstein, around in the first decade of the 1900s, so it was known in the early 1900s that light mostly acted like a wave. But then Einstein came by and said, no, light kind of acts like particles. And so we had this dual nature of light as waves and particles. Well, what de Broglie did in the 1920s was say it's the same exact thing with matter. Matter we mostly think of as particles, but you can also think of matter as waves in a way. And he wrote the equation that the momentum, which is usually called P, which is the mass times the velocity, he said that's equal to some constant called Planck's constant h divided by the wavelength of that particle. So we know that light moves at a high velocity. So if you increase the velocity a lot on this side of the equation, well, you're going to have a very small wavelength because this thing up here is constant. And in the same way, if you have something moving very slow, well, the wavelength is going to be very large. If you have, say, an electron, which the mass is very low, and you can calculate its velocity, you can calculate a wavelength from that too. And electrons were found to have the wavelength of electrons was found to be much, much greater than the wavelength of light. But this was the first inkling that, okay, things are getting weird. Is matter waves or particles? Is light waves or particles? A lot of the theories in physics were falling apart around this time, and that's what I'll be discussing in future videos. So thank you for watching, and I hope you learned something.